Okay, now let's do a deep dive in one of the YOLO architecture. It is almost impossible to go through everyone and every version, and that will be terribly boring. But I just handpicked version 8, and it's actually a very complex network. But don't get lost in the details here. It's actually easy. So what essentially the crux of this is, you are doing, you starting with an image, and then this is basically like resolution reduction in the image, the typical convolutional neural network path. So you reduce the size to 320 cross 320, 160 cross 160, 80 cross 80, 40 cross 40, and 20 cross 20. After that, you kind of upsample. Okay, but there is actually an interesting thing happening here. You are concatenating in between, and then kind of, we can say something like the residual connection, but very interesting aspect related to it, I would say. And before I go into the deep part of it, as I said, there are various options within a version. So for example, version 8 itself has various complexity levels. So n stands for the lightest network in terms of complexity, and X stands for the extra large version, and D is basically the depth module. This is basically the number of layers. If you have a higher D, it means the number of convolutional layers will be higher, more layer network, deep network. And W is basically on the resolution side, and R and W basically are on the resolution side. You can see here W is affecting the resolution, or the number of channels, either. And R is basically, in fact, I would say this way: W is basically the width, and R is the ratio, which is going to affect the size in terms of the width of the image, or the height of the image, in that sense. Okay, D is basically, it's not shown here, but it is inside this particular layer. Okay, so now with that, let's start what's happening. And before going in the high level overview, let me introduce some of the uh, components which have further layers. For example, the convolutional layer is not really convolution, it is convolutional 2D followed by Batchnorm followed by CLU, which is sigmoid ReLU kind of concept, or some people call it as leaky ReLU. So that is, so wherever you see this con block, this is the combination that is there, so always remember that. And similarly, the C2F is basically a interesting module. The C2F is commonly known as cross stage partial connections. Okay, so C2F module is basically cross stage partial connection. I will explain why it is named like that. So this is the module. So you see over here the convolution, again this is the convolution module full, and it is basically having 1 cross 1 kernel with stride of 1 and no padding. So this is just to kind of change the channel size from C in to C out, whatever desired size. Okay, so the input will become C out, nothing is changing. And next comes the interesting part. So this is similar to the residual connection, but it is slightly more complicated, or more interesting than that, because the channel C out is getting split into two. Half of it goes in this path, and half of goes as the skip. So the channels get split into half, and half of them will go into directly into the concatenation layer here, and the remaining half will pass through something known as bottleneck layer. And this bottleneck is actually nothing but a series of convolutional two layer convolutional network, just convolution. So this convolution again is this, so don't forget that. So it's a bit complicated, but this can have two options. So there's a shortcut. If shortcut is true, it is having a skip connection. If shortcut is false, it doesn't have this residual or skip connections. That's the only difference, and no change in height or width or channel number as it pass through these layers. So it is just to have few extra convolutional layers which is having these. So convolutional 2D layer followed by batch norm followed by leaky ReLU. So that is the layer which is two times here in the bottleneck. So, and this bottleneck also can have n numbers, and this is n which is coming from uh, basically the D, the depth here. So you can see n is equal to 60 or 3D, whatever. So how many number you want is decided by that. So if it's a very lightweight, you may not have many number of layers. If it is extra, uh, you care about accuracy and not on the lightweightedness, then of course it will have more, like 6 layers of bottleneck and so on. Okay, so the cross stage is partial is coming because of the split. Yes, partially splitting the channels, and one is taking the skip path, the other one goes through all these convolutional layers, and each time it is skipping, and then finally it gets concatenated. The number here is interesting here. The these guys actually creates n c out, 0.5 n c out rather, because c out 0.5 c out is there, but you are having n number of concatenations, obviously that will come, and one 0.5 c out will come from here, and the other 0.5 c out from will come from the last layer. So totally it will have n plus 2 c out. So uh, if you don't go by the number, what is going to happen is you have a rich number of layers getting concatenated at this stage. Okay, so that's interesting. So this is like a deep learning network which is happening here, and that's interesting thought around which the YOLO is built in. And then we have one more convolution. So the C2F layer, wherever you see it over here, and whenever the shortcut is true, you have the skip connection. Okay, so that's what exactly happening. Okay, and okay, and now if you see, there's one more interesting layer, which is the spatial pyramid layer, which is nothing but just the max pooling combination. So basically you are going to kind of have the image almost in fact the image is at a low resolution here, 20 cross 20 only, but even there you have multiple resolutions, and you're concatenating that and passing through a conv layer here. Okay, and after the concatenation you are kind of bringing it back to the same size. So let's go through this network after you know about all these sub networks here. And then of course I missed one part, which is the last part, which is the detection part, where the bounding box laws and the class laws are trained. It is actually nothing but a two layer convolution, just like this bottleneck layer. It's a two layer convolution, but with a kernel size of 3 and no stride, so no reduction in size is happening here. Okay, and in general the YOLO is kind of built into three parts. So this part, which kind of does the high resolution image to low resolution image but increased dimensional in the feature space, is known as the known as the backbone. So this guy is known as the backbone typically. So its job is to kind of extract the features at multiple resolution, and then this guy, which is kind of stitching it back to the original dimension or the desired dimension, is known as the uh, neck, and the top guy which does the detection is known as the head. Okay, similar like our human kind of structure, head. Okay, and now if I want to explain this, so let me basically go and explain what's happening. So you have an image taken at 640 cross 640, that is passed through a convolutional layer with stride 2 and size 3 cross 3, which will bring it down to 320 cross 320 with a channel number of 64, and this W is determined by the complexity of the desired complexity of network. So for example, if I take it 1, it is basically 64 cross 320 cross 320, and then another convolutional layer which further reduces it to 160 cross 160 but increase number of channels here, and then it passed through that cross uh, the splitting layer, this guy, and its output is not changing. But the interesting part is this will have a lot of convolutional layers. So three bottleneck layers here. So basically this layer will have three times here. So this is kind of residual, as I said, but it's not fully bypassing, but rather the channels are getting pushed through. Okay, and then the resolution is reduced to 80 cross 80, another C2F layer, then 40 cross 40, another C2F layer, 20 cross 20. So every convolution will reduce the size. It's strided convolutions, obviously it reduces the size of the image. So we can say this guy is increasing and this guy is going down. That's a typical trend, right? And the feature space is becoming high dimensional, but the resolution of the image is getting reduced. So this is exactly happening here, and it stops at this point, and then The SPPF, as we said, it's further does the without any learning. So there is no learnable parameter in this max pooling, but it kind of reduces the dimension of the feature, the resolution of the feature rather, but keep the number of channels same. Okay, now comes the upsample or the reconstruction part. Okay, so you have this 20 cross 20, it is going to the concatenation, and we will come to this part later, but that is basically going to a detection. Okay, so this is equivalent to like the SSD's multi resolution reconstruction that we were multi resolution bounding box prediction that we were talking about. Okay, so you have the size which is actually this size. So 20 cross 20 you can think of that is the grid size in the original YOLO. So that's it's the same, and this is basically the thing that has all the predictions plus the classes and the bounding boxes which is coming here. Okay, so this is that guy, and we have that for this resolution, this resolution, and this resolution. So that's the beauty of it. Okay, and it is not like it is directly getting thing, there is something concatenated here. So we'll come to this what is coming from here. So before that, this 2020 is upsampled to 4040 and is concatenated with the same dimension, because we have a 4040 coming here. So it's concatenated with this upsampled 4040 and this one. So you have basically increased, you concatenated this, and you have an increase in size here. So 512 cross W cross 4040 coming here, and 512 cross W cross R cross 4040 coming here. So if you add them, add this guy and this guy together, there is a 1 plus R term getting increased. So that dimension is kind of increased in that sense. Then it passes through a C2F to make it back to like this dimension, and again upsample it to this dimension. So 80 cross 80, but again added with these two. So 256 plus 512 will give you 768. So those many channels here, but again this guy will reduce it to 256. But now this 256 cross 8 cross 8 is also used for detection, okay, which predicts the classifier score as well as the regression here. But the interesting part comes here. So you see here this 40 cross 40, it is also going to a concatenation layer, and this guy 80 cross 80 is further downsampled and passed it. So it's like interlinked kind of network. So it's concatenated here, and this 256 plus this 512 will make it 768. Again this C2 layer is used to reduce the size to 512, and again passed it through this to kind of increase the or reduce the resolution. And this 2020 we earlier skipped this step, it is combined with this. So you can see here these two are concatenated, and you can again see there's a 1 plus R coming, and that is passed through C2F to reduce to whatever desired size that we want. Okay, I think there is a small typo here, the dimension is actually kind of missing here, and if I remember correctly this should be 512 cross W cross 20 cross 20. Okay, so that's a number here. Okay, so what is the essence which is happening? If you don't understand any of the inner layers, or you don't care about the inner layers, this you should not miss. Okay, so let me just write it here so that, okay, so this is important. So 20 cross 20, 40 cross 40, 80 cross 80. So three different resolutions of the feature map we are having predictions, and this 256 cross W is basically including this particular bounding box and the classes. So it includes that. So it depends on the classes, how many classes are there, the remaining will be so I think it's easy to predict. So probably the 4 or 5 will be the bounding box parameters, and the remaining will be the classes that it's going to predict in this dimension I'm talking about, right? Because if you remember earlier case, so 30 cross 30, or rather it's not this, so 7 cross 7, the YOLO version 1 I'm talking about, cross 30, right? This 30 had 5 bounding box parameters plus C was 20. Okay, 20 plus 2 bounding boxes per this. So 2 into 5, 10 plus C20. So 30 was there, this number. So similar to that, you can find it how many of them basically out of this 256 cross W, if I assume W to be 1, assuming this guy, if it is 1 like the L version, then this is basically 256 cross the resolution. I don't care, it's too much. So this 256 should ideally have this equivalent to this. Okay, so that's all about YOLO V8. And for you to further study, so I just put the evolution of all the object detection right from these were traditional machine learning methods, you can ignore that. So from 2012, since the onset of AlexNet, we know that convolutional neural networks became popular. There are two lines of work. One is one stage detector, which is end to end, and the other one was two stage detector. We discussed about RCNN up to faster RCNN, but you can actually look at other options. And then SSD and YOLO and all versions of YOLO, we had a brief discussion. But there are other networks which are interesting, like RetinaNet, for example. This is a very popular network. CornerNet is another one which is very popular. And you can take a look at that for self study. And then of course there are transformer based object detection as well, like swin transformers, which we could potentially discuss when we discuss about transformers in the later class. And just to show you the quantum of development in this field, you can see that till 2012 it was a reasonable number, still it was 500 publications per year. But you see 2021 it is 3500. So it's mostly application. It's not like radical developments in the architecture or any new object detection methodology is coming. This includes kind of applications also. So that clearly shows this field is evolving and still it's very popular in that sense. Okay, and when we go for object detection, we generally never do anything from scratch because too many things, too many variabilities. I have a slide next coming up on the variability side. So better to rely on some open source implementations. Facebook has this Detectron, which has many models built in, and Torchvision also has a few models built in. You can have a check in that. In the lab, we might try to do everything from scratch for our learning, but I would not advise that when if you working in the field. Okay, so to summarize, so object detection, it definitely is a harder problem. I hope you appreciate it by now. It appears to be an easier extension for classifier, but that's not the case. Okay, so there are near infinite. So this is what I was talking about. You can keep on improving the object detection in many ways. You can have better backbones, right? Because you always have a backbone which extract the features. So you can change that. You can come up with pre-training with many data set and many image transforms. Is always a variability. Then the head and neck part, so the backbone is one aspect. The head and neck, we have many approaches in RCNN and its variants. SSD and YOLO also produce many variants on that. And then of course you can have concepts, many concepts, and even we didn't discuss the losses or loss functions in much details in this section. But all these are the variabilities, and hence it's actually not easy to come up with an object detection neural network or convolutional neural networks for object detection from scratch. And if you are interested, please have a look at this paper where they are playing with all these and see that you can speed up the training, you can improve the accuracy in training, but the inference time speed is tough. So improving the inference time speed is really tough. And we could confidently say that YOLO and its variations have been a good trade-off between the accuracy and the speed up that is possible. Okay, so I hope it's pretty clear. And even though there's a lot of confusion about the object detection, how to go about it, I hope I was able to convey a clear cut reasoning for what these different models stand for.